This brings us to Professor Nino Cucchiara, Antonino from the College of Marin, and I'm entered full screen when you shared your slides, so I lost the title of your talk, who will talk about following the Grace Roman telescope in the exploration of the most powerful cosmic explosions. Nino, off you go. And
Thank you much. Thanks, Fed, and thanks everybody. I want to thank the organizer for calling me this task that I kind of face humbly. So my title is Exploring the Most Powerful Transit with the Grace Roman Telescope. Some of you know me as Nino. I'm a College of Marin, and I'm going to present an overview of gamma ray bursts science. And I want to point here in the spirit of the Nancy Roman Telescope. This is a sort of also an honor to the long list of women and men and colleagues that shaped this field up to today. And I apologize already if I, didn't cite you or cite others that I might forgot them. Some of the work here has been also, some of my work has been funded by the National Science Foundation, NASA, and I'm also part of the Vera Rubin Observatory Transient Variable Star Science Collaboration and a member of Justice, Equity, Diversity, and Inclusion Working Group. We were supposed to be all together in Pasadena, and so I want to do a land acknowledgement because a year passed from a day of action in our field, and I think we should not forget what we learned those days. So I just read it aloud. We acknowledge that we are located in the ancestral lands of the Hamogna tribe of the Tongva people who have stewarded this land throughout the generation. We honor the gratitude of the land itself and all its ancestors, past, present, and emerging. We thank them for their strength and resilience in protecting this land and aspire to uphold our responsibilities according to their example. And we also support actions and policies that focus on the reparation of the harm caused to these lands and their ancestors. And I found these acknowledgements usually useful also in these times where we see a lot of our space as the space be also a new land of appropriation. Anyway, my outline here is for you. I will talk about the gamma ray burst in general. I connect GRBs and supernova for you and how GRBs can help find the first stars, how we can use them to trace star formation rates at redshift larger than 7. I will focus a little bit on short gamma ray bursts. And of course, I cannot forget the contribution of gamma ray bursts on our study and knowledge of kilonova and gravitational waves. And I'll finish with some reflections on the Nancy Grace Roman Telescope in light not just of the science, but of the Decada survey. So here's a slide that kind of summarizes a little bit of gamma ray burst infants time. They were discovered serendipitously by spy satellite Vela, and they were detected as coming from outside the orbit of the moon. Here see the usual image of gamma ray burst as with a pen, the brightest object in the sky. And then, of course, thanks to the work done by the Great Observatory, CGRO, and the BATSI instruments, we knew this object must have been cosmological. Okay. In the following years of the early discoveries, thanks to the follow-up of satellites like XMM Newton and, of course, HST and Chandra, we were able to actually identify not just the high energy emission, but also the low energy counterparts that we call the afterglows. And these will show up, of course, in X-ray, optical, and later in radio. Now, with the limited capabilities from space, based on, for example, the slewing time of XMM Newton, 8 hours, or HST at the time, the ground-based community kind of came together to follow up from the ground gamma ray burst. And this was the first time, I think, that we all kind of put together a worldwide collaboration to understand these tremendously powerful objects that are in the sky. So here's a quick history, again, on what we think a gamma ray burst is. There is some sort of collapser. Can everybody confirm that you can see my arrow on my on my screen?
Yes, we can see.
Thank you. So this is a kind of an old slide, of course, but the main idea is there is a central engine. We'll talk about that in a second. That produced during this event a jet that eventually produced this ultra relativistic jet in shells. Some of the shells collide. They produce the internal shock, which will eventually produce the gamma ray emission that we all see. And then the interaction between this jet with the interstellar medium or the surrounding medium of the progenitor will eventually produce what we call the afterglow here. Okay. So I just point here a reference of Peter Mezaros, but of course there are many references that are not included in this work. Now, thanks of this preliminary idea, NASA and many others have designed a spacecraft called the Neil Gehrels Space Observatory, formerly known as SWIFT. And thanks to SWIFT, after 17 years and counting, our tremendous work for a SMEX mission, which has been #1 mission for many years now, from the decadal surveys and the senior reviews, actually. We now know that, for example, we have a huge data set of X-ray likers. What first was just a single power law before SWIFT now has been much more complicated. We have the prompt emission, we have steep decays, we have different type of late times peaking like 1,000 seconds, which were unthinkable before SWIFT, of course. And thanks to this information, not just in X-ray, but also in other wavelengths, we have a better sense. And of course, when you get answers, then you have more questions coming up, right? I just want to remind you that SWIFT is the unique instrument satellite that contains three telescopes: a gamma ray coded mass camera, a optical UV telescope, and the X-ray telescope together. And the slewing time for these satellites is in the range of a minute. Now, when we look at the progenitor, and we already from the gamma ray data provided by Batze in the 70s, we kind of distinguish the gamma ray burst as long and short. Long typically have a prompt emission, gamma ray emission longer than 2 seconds, short less than 2 seconds. And these immediately led to the knowledge of what type of progenitor we might have. So for the long one, we think there are compact objects, collapsers type of objects. For the short one, there might have been the mergers. Sorry, I forgot to run my clock here. So I'm a little bit bad. Compact objects could be neutron stars black holes, black holes. Okay. Now moving forward from Batze times and using also the data from SWIFT, we have now kind of I'm not saying an evidence, but a hint that might be a third category of in the intermediate class of GRBs over here. And this work by Sumit et al. But also we have the evidence that there are ultra long GRBs for which the prompt emission or the gamma ray emission lasts longer than 1,000 seconds. And that, again, as I said, you get an answer, you get 10 more questions, right? What is the central engine of this very long, ultra long gamma ray burst? Okay. So overall, you can think at this, at level 0, the long gamma ray bursts are produced by collapsable massive stars around 30 solar masses or more, and the short gamma ray burst can be a byproduct of compact object mergers. Now, GRB in a nutshell. So all of you might have seen this before. Gamma ray bursts represent the most powerful explosion in the universe as a single event. Their interaction, as I said, the afterglow is an interaction between the outcoming jet and the stellar medium, allow us to actually test and identify what material is in the surrounding medium, which we call the host galaxy. And that allowed us to determine the chemical enrichment of the history of the universe. The fact that gamma ray bursts are so powerful make them visible at redshift 20. Again, these are single star objects, right? So maybe they're pop-3 stars, maybe they are the signature of period instability supernovae. These are all questions that we hope to answer at the time of JWST, but of course, Roman telescope as well. We already know that short gamma ray bursts are connected with the production of gravitational wave signals. But again, this was not known until 2015, 2017. Overall, they represent our best tool to study the early stages of the universe, but also star formation, ray density, the property of reionization period, and so on. And then because we have now came to this, with this concept that the short gamma ray bursts are produced by these compact object mergers, and we can think that these are laboratories for very late stages of the stellar evolution. We can study the magnetic fields around the stars. We can talk about shocks, equational states, and of course, magnetars. I'll get that in a second. Again, long gamma ray burst, briefly here, connected in many ways with magnetars, black holes, supernovae. Even though we said that long gamma ray bursts are the progenitor of single massive star collapse, and there are, we know there are interaction between these jets and the environment. And for example, we know this is jetted, and the jets and the emission is also polarized, right? So there is polarization studies that are at the very infants at the moment, even though we know about gamma ray bursts for a long time, mostly because the technology wasn't there, because the follow-up required didn't provide bright enough object to look at through polarization. So, but that definitely is a field and an aspect that we can explore, and we will explore in the future years. X-ray light could represent flares, which and also precursors. So what does it mean? It means the central engine is not just a one-off. There is a late activity, there is an early activity. So these are all the questions that we hope to answer, and we don't have a clear answer at the moment. Of course, gamma ray burst, long gamma ray burst end up as black holes very likely, and we have evidence that gamma ray bursts are also associated with supernovae, 1C type supernovae here that suggests a common origin. And remember, the gamma ray burst can push your envelope of redshift, a very high redshift. So understanding even better what supernova 1A, sorry, 1B, 1C, and long gamma ray bursts do together can be very informative for both fields, the supernova field, the cosmology field, and of course the gamma ray burst field. We need large field of view and high energy instruments in space to make sure we detect them. Here's a map from the Fermi GBM catalog here, and this is the redshift distribution up to a few years ago. And we need to detect gamma ray bursts, long or short, geographical, really rapidly within a minute or so, because the instruments that we use for follow-up from the ground base, for example, have sensitivity limits, right? So we need to get them within a day in order to obtain both redshift measurements, understanding the progenitor, and then study the host galaxies, and eventually understand the interstellar medium and the intergalactic medium between us and the source. So getting ready for these new GRB searches in the time of Roman, I think is exciting. I'm really excited. And now, I'm an optical astronomer. I do follow up from the ground for the last 15 years. My phone has never been off all this time. But now I'm looking at this slide. I was making this slide the other day, and I'm saying, wow, this is fantastic. We have Vera Rubin Observatory. We have SKA coming online, which also will allow us to detect afterglow in the radio very early on through this large field of view survey in the radio, right? Of course, JWST, the neutrino component is becoming more and more important, and I can't imagine this to go away. Actually, improve the importance of this. And of course, this is my favorite telescope, the Gemini telescopes, where I did most of my research in the past and present. And so the synergy between these multi-messenger time domain facilities from ground base and space will be the only key, and will be very promising for our studies on gamma ray burst. So here's some information about Roman and light curves along gamma ray burst. Here in this yellow area here is where Roman can actually start observing. According to the latest program level requirement, Roman will be able to slew to a source within 2 weeks from notifying the Science Operations Center, according to if the object is visible within certain constraint, of course. And that's the lander you see here. But look at the limit. This is a 50-second limit in the F87 filter here. And so you can see that long gamma ray bursts can be detected even just a minute in the optical. And of course, due to the synchrotron emission of the afterglow, it will be even brighter in the infrared. So even though if we go down 2 weeks or 3 weeks, we're still able to see gamma ray bursts and be able to take rhythm spectroscopy, which will enable not only just taking the redshift through simple Lyman break technique, but also study DLAs. Okay, I will not talk about damp laminar alpha system in this talk. Now, what will we learn? A lot, right? So here's a compilation of many X-ray luminosity and LAT, again, from the Fermi satellite here. Lots of light curve. These are lots of supernova bump from Close et al. And here's some more from Cano in 2017. We will be able to probe, thanks to the late time behavior of the gamma ray burst, finally we'll be able to probe the existence and the nature and the role the jet breaks play into the afterglow emission at all. We'll also be able to study the unobscured emission through Roman and the infrared filters. We, of course, we already said about redshift and talk about the supernova association. We talked about magnetar briefly early on, and here's some summary of where magnetar play a role in our GRB schema of things. And of course, you can see here the typical afterglow here. Sometimes these are all X-ray light curve in general. There is a plateau oftentimes that can be indicative of a magnetar here. The steepening decay after the plateau can be a collapse of the magnetar into a black hole. Okay, so understanding this property, and this is just in the X-rays. So here you see some more work on how these bumps here have been associated. These are all long gamma bursts to the contribution of magnetar emission. Of course, I cannot give a talk on gamma bursts without exploring the hierarchy of universe. Here's the spectrum. Believe me, this is a spectrum from Symphony on the redshift 8.2, and this is the Lyman break here. This is I agree with you. This is a crappy spectrum. I'm not gonna lie. Okay, but it's been taken at 20, just at 24 hours after the GRB happened. Okay, when you look at the Roman capability, that's the blue line here, and this is the infrared light curve of that same GRB. You see that the gate, the ball is in our court. We can do a lot with Roman if we have an understanding. This can be a hierarchy of GRBs, and I'm willing to wait 2 weeks until you get a very decent data points here, understand what it is, and even more, I'm waiting to get a Grism and get a much better spectrum here. So Lyman break techniques will be the key here. A broad feature like diamond Lyman alpha feature will be a key. The Lyman break will be key through the Grism, and of course we can do some other studies to some level of precision, of course. Now, star formation rate density, of course, is an interesting. We'll see more about this in the next years, thanks to JWST. But again, gamma ray bursts already provide some interesting results that kind of match this puzzling discrepancy from sub-millimeter studies where the star formation rate density, the unobscured star formation rate density, is higher than the model predict. Okay, Roman will be complementary with JWST. And thanks to the TO capability, the target opportunity capability, and the capability to slew, within the certain observing constraints, they are complementary to JWST. Hopefully, we will be able to nail down more hierarchy GRBs. Hopefully, short gamma ray bursts. I'll be a little bit quick here. Again, the emission is shorter than 1 or 2 seconds. The emission is very faint compared to a long one. It's very hard to localize them. And then the short gamma ray burst and association with their host galaxy has been very difficult, although, as you see in a second, a lot has been done. We know they're produced by compact optical measures. They produce, so they are the electromagnetic counterpart of gravitational waves, of course, but also a kilonova emission, something that was predicted for many years and detected in 2013. And that's, everybody talk about this as the where golds come from, where these heavy elements come from. So I'll get that in a second. Let me go to the basics here. This is a comparison. The black lines are a short gamma ray burst light curve in the optical compared to the gray one, which are long. So you can see they're intrinsically fainter. This is the very first association of a short gamma ray burst with a host galaxy from Derek Fox. Here's a work done by Wenfei Fong here. And I just want to highlight the work of Wenfei here, because there is a long generation down to the youngest one here, the graduate students, and they're working on these fields. So the future is bright. More data are collected, and I'm really excited to see what's going to happen here in the study of short gamma ray bursts and their association with their host galaxies and gravitational waves. So here's the redshift of the first short gamma ray burst that led to the kilonova detection, the very first kilonova detection. And again, I'm thinking here that this is going to be more. We have more of these events, and gamma ray bursts can really play a role here. Look at the brightness here and where Roman is actually going to fit. We lost it here, right? We lost it because it's beyond the capability of HST. I'm going to be very quick here in the model of the kilonova, neutron star mergers here. But this is the image that I want to highlight here. These are 4 different chemical elements in the infrared, and these features, they're very broad. So we really hope that the Grism will be able to actually capture some of these features of kilonova features with Roman. We care about gravitational waves and detections. Here's the landscape in 2026. More detectors, more accurate localization. Thanks to Roman, we'll be able to tile some of the most significant and smaller banana shape, there are no bananas anymore, error circle here, and finally get the handle on the electromagnetic counterpart of this GW event. So the landscape, I mentioned earlier that Swift was a great success. It still is. Long live forever. The next Grace Roman telescope will require a multi-messenger approach in order to do gamma ray burst study. And I mentioned here some of the missions that either have been proposed or have been are already in planning. So the good thing is that JWST is up. The bad thing is that something has been happening. We know there are mistakes have been made. And I just want to say this, that it's important to think that the Roman is an opportunity. It's a great opportunity for us to move forward, and the decadal 2020 recommendation brings us to really core values. We need to consider this, our professional societies, and I be sure that our integrity is maintained, and that includes also situations that are led to conflicts. So it's an opportunity to inspire new generation of astronomers, more than Hubble, more than JWST. And what we plan, and await all this great research that we see in these talks, I just want to remind you all that we cannot separate equity and inclusion from the research and the action that we take. I will leave my reflections here, kind of a conclusion, and I'm open for questions. Thank you.
Great. Thank you. Perfect timing, as always. There's a couple of questions. There's two questions from Ranga, one on the chat and one on the Slack. I will go with the one on the Slack that is more physically oriented. Has anyone assessed if one can get gravitational waves from collapsers? After all, we know the collapsers are asymmetric because it results in supernova with kick velocities.
I don't know, honestly. I don't have the answer to that question, to be honest. And I don't know if anybody, I know Igor is here, maybe is more up to date on the, I do believe that we will know more, right? There are more gamma, there are new LAGO events that are being published late after the reprocessing and so on. But I haven't seen any paper that, match electromagnetic counterpart of possible counterparts in the gamma rays, for example, that lead to that conclusion.
And also from Ranga, what is the primary constraint for Roman not slewing somewhere faster than 2 weeks? 2 days will be very compelling given the other capabilities of Roman, and no multi-messenger mission can compete.
So I see Julie kind of gave a response here.
Yes.
I think, Ranga, there are a couple of things here to consider. First of all, Swift is in a low orbit, while Roman and JWST are in L2. So there is a necessarily delay due to the orbit itself. What are other constraints are probably orbital. There are some areas of non-observability, depending which period of the year you are. And please, Julie, feel free to jump in if I'm saying something completely stupid here. But I agree with you, Ranga. It would be great to have something much shorter time scale, but we have to play with what we have.
Excellent. If there are no other questions, I'm waiting for instructions on what is going to happen next. There is one where we finished just in time at the end of the session. Let me just check that there are no further questions on Slack. As you know, we have a discussion today later in the day, so we can bring our questions there as well. And you can always reach our speakers on Slack. Actually, Igor hasn't answered or more comments on the original question, which I'm going to briefly read. Yes, collapsers can be generated. Gravitational waves can be generated by collapsers, but probably they will be detectable only in our galaxy or very nearby universe. Thank you, Igor, for helping us out. We have one pop-up poster, so I'm going to pass the mic to somebody else for that. I just want to thank the speakers in this session. They were terrific, and we finished almost on time in spite of technical difficulties. Thanks, Nino, for your last talk. I don't think I encourage people to give a round of applause, but please give a round of applause to Nino. And thanks, everybody, and thank you for giving me the opportunity to chair the session.